So the topic of my talk tonight is a history of computers and chess, and along the way, or as an integral part of that, an explanation of artificial intelligence and how artificial intelligence developed recently, the last several years, and in particular the application to chess. So the title is a little bit of a joke. So 22 years ago, I wrote The Complete Idiot's Guide to Chess. It was the last thing I did as a professional chess player. And the book actually has been in print ever since. And in fact, the publisher, which is now Penguin, approached me about 8-9 months ago, maybe 9-10 months ago, and they asked me. They said, we're rebranding the whole Complete Idiot's Guide series brand, and we're beginning with a couple of titles, and we'd like for your title, the chess book, to be one of the ones to begin with. And so they are rebranding it How to Play or How to Do X Like a Boss. Not my choice of title, it's their new title. So the book, How to Play Chess Like a Boss, actually is literally on sale in the next few days. And I spent a couple months sort of updating the material of the book, and I spent particular emphasis on the chapter on computers and chess, because obviously that was somewhat out of date some years later. So my guide is the guide from a complete idiot to you, as I taught myself quite a lot about computers in chess, and in particular artificial intelligence. So moving ahead. So there's a very long history of chess being significant for computer science, going all the way back to 1949. Claude Shannon, who was one of the preeminent computer scientists of his time, wrote a paper where he specifically argued that chess was an ideal problem for computer scientists to really focus on in order to develop what was then sort of a nascent and evolving computer science knowledge. And he specifically called out 4 reasons. The first, the problem is very sharply defined in terms of the allowed operations and the ultimate goal. Right? So you want a problem that's really sharply defined for computer science. The second is, on the one hand, it's not so simple as to be trivial. We're not talking tic-tac-toe. But on the other hand, it's not so difficult to be intractable. It was a problem that you could imagine 70 years ago that computers could somehow really gain traction, address, solve, and whatever it would mean to solve chess. The third reason is chess is a thinking game, right? And this is important because it means that if the methods of computer science could be applied successfully to chess, it would either have to force us to admit the possibility of mechanized thinking, or it would really force us to reconceptualize what thinking is, what we mean by thinking. So not only is chess a well-defined problem that was difficult but not too difficult, it was also one that could be meaningful. And then finally, the discrete nature of chess was very important, right? It's a very sort of binary game. There are specific moves, specific outcomes. It's not just well defined; it's sharply defined in a way that really is important for computer science. And I would argue that it was a really brilliant insight, because not only has chess proven to be very fruitful for computer scientists, I think it continues to prove so. So 70 years later, chess still is a very useful problem for computer scientists, as we'll see. So a few things that kind of characterize the early history of computers and chess. The first, and it's important for us to remember this, there was actually a very sharp debate between whether brute force, which is the method that actually turned out to be the most successful for decades, should be applied, or whether artificial intelligence should be applied. Now, artificial intelligence is not actually a very well-defined term, and we'll come back to this in more detail later. It really just sort of describes a whole different set of approaches. But in the end, brute force was actually the approach that really worked. It turned out that even though at first computers sort of using specific algorithms. By brute force, what I mean is you're writing the algorithm, you're telling the computer exactly what to do, how to search, how to evaluate, how it should choose a move, or what rules it should apply to choose a move in each position. At first, it turned out, to be a sort of very rudimentary level, but it kept making very steady progress for a very long time. Initially, it's kind of funny. There were very over-optimistic projections by computer scientists, and at the same time, there was almost complete complacency by chess players, such that I'm 51 years old, and I remember even in the 1970s and the early to mid 1980s, there really wasn't, like, chess players just didn't think about computers really being meaningful as potential opponents, or now as engines. Obviously, we use them all the time. And I use this example. The renowned computer scientist Herbert Simon predicted in 1957 that a computer would be the world chess champion within 10 years, right? So on the one hand, he was obviously wildly over-optimistic. He was off by 3 decades, but he was right. And at the time, and for a few decades afterwards, chess players somehow didn't even really internalize the possibility that a computer would be the world chess champion. What I have here is a chart that I found as I was doing my research. And obviously, you shouldn't take these estimated ratings as, specific point estimate. They're sort of rounded estimates. But it's actually surprising how accurate it seems to be. And on the right in the notes, I've noted a few very sort of salient items for each time period that helps us fix what the relevant strength of the computer was at the time. So as we see, there seems to be a pattern where roughly every 5 years, the best computer in the world is gaining about 200 ELO points. And what I've done to try to contextualize that is show, well, what's the expected score of the best computer in the world versus the world chess champion, if we assume the world chess champion has 2,800 rating. And of course, as you can see, for many, many years, the expected score is 0. So you could just sort of like ignore this thing happening over on the side. In 1978, the international master David Levy quite handily defeated probably the best computer in the world in the 1978 match. I don't know what David Levy's ELO rating was, but if we assume it was around 2350, let's say, and let's say he was probably playing a strong A player as an opponent, then sure, that makes sense. He didn't just win every game, but he sort of won handily, right? 5 years later, or maybe 5-6 years later, Feng Shui, I'm not going to pronounce his name right, I apologize, but Xu and Murray Campbell start working together on the Deep Thought program. And by 1988, Deep Thought begins competing in chess tournaments. And I'm actually old enough to remember when Deep Thought started competing in chess tournaments. So I remember Deep Thought being beaten very handily by Walter Brown. But on the other hand, Deep Thought defeated Alex Fishbein in a game. And I actually specifically remember it was a rook and bishop versus rook endgame. And you could watch on the computer screen the computer's evaluation. And at the very end, when it was a forced checkmate, there was actually a message that said "search terminated," which I thought was kind of a funny thing. But so we see that, yeah, 2400 seems about right. This computer's competing, and it's not competing at Grandmaster level, but it is able to hold its own against strong masters and occasionally even beat fairly strong senior masters. In 1995, let's say roughly 2600, okay, well, Garry Kasparov won his first match against Deep Blue 4-2, right? Obviously facing a very significant opponent. And then, of course, as we all know, a year later, he lost the second match, 3.5, 2.5. Now, I was there for the second match. You've probably played over the games. I would argue that Garry Kasparov really over-prepared himself and to some degree psyched himself out in that match. He really tried to play chess openings that were somehow playing against the computer's weaknesses rather than simply playing the openings that played to his strength. And so the 2 games that he lost, there was a Ruy Lopez, which he just had a very passive position. and then this disastrous Caro-Kann where he allowed a well-known sacrifice in the opening. He just thought the computer wouldn't sacrifice a piece for position, but it did. It had a tremendous advantage, and he just sort of lost a very poor game. I think if Gary had been playing up to his true strength, I think he probably would have won the match 3.5, 2.5. But we can see he's playing an opponent that's roughly his level. 5 years later, one of the best computers in the world scores 3.5 out of 4 games against 4 very strong grandmasters in a tournament. There was another computer, Hydra, that beat the Grandmaster Michael Adams by 5.5 halves. So at this point already, by the middle of last decade, the best computers are sort of surpassing Grandmasters. And of course, afterwards, computers just keep getting better and better. And now it's not even worth Magnus Carlsen playing a match against best computer in the world, because he knows he'd just lose almost all his games. So we're going to have a very quick primer on how sort of the method that developed chess computers all the way from the 1950s, really until just a few years ago, works. So chess players in the audience, first one, raise your hand. Who can spot the force win? All right, I saw your hand first. What is it?
Knight F7.
Knight F7, and then after king, well, if rook takes knight, then what? Okay. So after king g8,
And Knight F6.
and king h8, and knight f7, right, checkmate. Okay, now, how did you solve this?
Check, and it's all forcing. It's all check.
Okay, and you knew the pattern. Okay, so you looked for a check. You saw the pattern of the forced checkmate. Probably also you noticed that the queens are opposing each other. So the key thing you had to notice is knight f7 check. If rook takes knight, queen takes queen, and then after that you just see the pattern, right? Now that's not how the computer solves this position, right? So how does the computer solve the position? Well, the computer lists out all of the legal moves, and then it just starts searching every single one as far as it can go by evaluating the sort of terminus position as far as it can go. And then it backtracks to choose the optimal move. How does it evaluate the position? Well, it has these hand-coded, handcrafted evaluation rules that are actually really, really complex and sophisticated at this point, because it's literally been developed over more than 50 years. And there are also some selective search techniques that are applied, right? So in principle, the computer is listing out every single legal move, and then every single legal response, and then every single legal response, and out, and out, and out, and out, and out. But because that tree multiplies exponentially, right, and it gets so large so fast, there are some methods for pruning the tree, and there are some methods for selectively looking ahead, or like one extra move, or prioritizing some moves over others. But basically, fundamentally what it's doing is it's brute force listing out all the moves, going out as far as it can, applying its handcrafted evaluation function, and then working back. Like tons and tons and tons of work have gone in to optimize it, but fundamentally it's the same approach that's operated for decades. Now, one of the things that can happen is what's called a horizon effect. So we have another chess position. Who can find the win? Yes?
G6.
Queen g6. Now, it took you a little bit longer. Why? It's actually much shorter. It's only 2 moves. The last one took like 4 or 5 moves.
That's your queen one move.
Yeah, because it's a weird position, right?
Yeah.
It doesn't look like a smothered mate. It is a smothered mate. It just doesn't look like one. By the way, for those of you who want to sort of geek out, it may look at first like queen takes h7 also works, because if rook takes knight, queen h5 check, king f8, queen h8 mate. but actually after queen takes h7, bishop b4 check, and then whatever response, rook takes knight. And actually, black has a winning position in that because of the material advantage. Now, granted, this is a bizarre position. Why is there no rook on a1? How on earth would this position arise? Like, okay, we get it. It's a weird position. But in some sense, that's the point, right? To us humans, even though, you solved this position after maybe 20 seconds, it did take you probably an extra 10 seconds or so, even though it's actually a much shorter search. For the computer, it would be much faster. I mean, obviously at this point, we're talking probably fractions of seconds, but still, because it has to search much less far. But another thing I want to emphasize in this position is the horizon effect. And the horizon effect is, well, what if, yes, this is a weird position, but hypothetically, somehow the computer got to this position in a search and said, okay, well, obviously black is winning this because, this position is, massive material advantage. But if it could just look one move farther, it would see that there's a checkmate. Now, in point of fact, there are particular heuristics that computers use where probably that wouldn't, in positions like this where pieces are on pre's and so forth, it actually has rules to tell it to look ahead one more. But the general idea is that this horizon effect had for many years bedeviled computers. Eventually, the computers got so strong that it was no longer relevant because the computers were just better than humans all over the place, so we were never pushing them up against their horizons. But it's still an intrinsic element to the brute force approach, right? Intrinsically, you're covering everything, but you're only going out so far, and you can reach that horizon. And what I want to show you later on is actually, I think, AlphaZero was there was actually a very sort of sophisticated way in which Stockfish ran into a horizon effect in AlphaZero, which I'll show in one of the games. But for now, I just want to fix this idea like, okay, there's this horizon effect that is just an intrinsic element of the brute force approach. All right, now let's start talking about artificial intelligence. So as I was saying a little while ago, artificial intelligence is a catch-all phrase. And it really just sort of describes any attempt to program computers to simulate thinking. And I put thinking in scare quotes because we're not going to try to define thinking, right? But just sort of, let's just say, doing something without relying upon explicit input-output rules. There were lots of different approaches, but the current wave, AI wave, and by the way, I should say, there have been periods of time when we have had excitement around AI. It's hard for us to remember this, but there was a lot of excitement around AI in the 1970s. There was a lot of excitement around AI in the 1980s. I mean, self-driving car, right now there's a lot of excitement around self-driving cars, which I personally think is actually has gotten ahead of itself. We've had self-autonomous vehicles of some sort or another for quite a long time. So there have actually been sort of waves of excitement around AI. But this current AI wave is really much bigger than before. And I think there's very legitimate reasons. There's tremendous capabilities that artificial intelligence techniques have been able to produce. And it's based on a specific approach called machine learning using neural networks, which I'm going to unpack in a minute. So for the moment, let's take a look at the box on the right, where I want to contrast traditional computer programming with machine learning. So let's not worry about what the machine learning is. We're going to unpack that over the next couple of slides. At the top, we have traditional computer programming, right? So for example, this is how all computer chess programs before AlphaZero really operated, basically all. You have handcrafted rules, and you feed in input, and the rules operate on the input to produce the output. With machine learning, what you do is you feed in input and you feed in sample output. And then there's a process, And there are many different machine learning processes, but as I'll describe, it's neural networks that's really sort of produced all of the progress over the last, during this decade. But whatever process you use, there's some process of machine learning which then produces its own rules. Those rules then can operate on fresh input to produce new output. But that's the contrast between traditional computer programming and machine learning. Now let's start to unpack what we mean by a neural network. Words sometimes carry meaning, or let's say associations that may not be accurate to the topic at hand. So forget whatever associations for the moment you have with network or neural. The word network here just refers to the way the inputs and the manipulation of the inputs to sort of interim output and final output is related. Specifically, you have arrays of data which are manipulated using linear algebra. That's basically all we're talking about. It's just the mathematical relationship of the inputs and the manipulations of the inputs to the final output, which at its core is linear algebra. The word neural is basically a metaphor. It's a reference to how neurons are thought to function as a network in the brain. But we really have to, we're not going to talk about the brain, we're not talking about neurons anymore in this. And I really have to emphasize, we have absolutely no reason to think that neurons in the brain are operating using linear algebra, right? It is absolutely just a metaphor. It's just a description that's kind of colorful to help us understand what this network is. It doesn't actually describe in any way the way it functions. And then there are two key tools at work, which we're going to get to in a few minutes. One is I talked about these arrays of inputs, right, mapped to intermediate ultimate outputs, basically using linear algebra. And then secondly, we'll get to this in a couple slides, backpropagation, which measures the fitness of the actual output to the desired output using gradient descent. And we'll unpack what all those words mean in a couple minutes. So why did neural network-based machine learning become all the rage? It's not a new technology. That's actually kind of the funny thing. It was really first developed like back in the old days, back when they were debating what approaches to use to apply to chess. And this key breakthrough of using gradient descent for backpropagation, that developed over 20 years ago. So it's not that some new technique was developed really. I mean, obviously there have been refinements, but it's not really like there's some big breakthrough in terms of the techniques. It's really, first of all, the hardware got good enough, fast enough, powerful enough that you could build dense enough networks that once you got to a level of density, and I've been told that for whatever reason, sort of six sort of intermediate layers turned out to be like this tipping point. I have no idea why. And then the second reason is you had these huge data sets, partly because you were accumulating decades of knowledge. For example, people have been, there are huge libraries of cat photos that people have been using for AI for a long, long time. But really because of the internet, and really because of the big internet giants like Google and Facebook. And they started building applications that were good enough for people to use. And then once people started using them, that generated more data, which made the applications better, and you got this positive flywheel going. So these are really sort of the two big things that happened. And that's what got this sort of revolution going. And in a couple slides, we're going to come back to, and we're going to unpack, there are two sort of key flavors of machine learning. There are two sort of different types of machine learning, which it's important to understand the distinction between them to understand AlphaZero. One is called supervised learning, the other is reinforcement learning. We'll get to that in a minute. But first, let's talk about backpropagation and gradient descent. So what we've covered so far is what basically machine learning is, what basically a neural network is, that we have this way of organizing the data And the way the data is manipulated is you sort of, the inputs and the outputs, you feed them into the network. And then you get to the end. But when you get to the end, there needs to be this feedback mechanism. It needs to go back and somehow inform that network to change the way that network is organized to make it work better. That's what back propagation is. So you start with an input X, right? It goes to a certain layer, right, which is just a data transformation, right? And there are weights. So let's say what we want to do is we want to recognize an image. Let's say we want to recognize cat images. And remember, everything is digital here, right? So when we talk about a cat image, like when you talk about, well, when you think about learning to recognize what's a cat and what's not a cat, you think in terms of whiskers, you think in terms of sort of the proportion of the body, maybe sort of the way the face looks. Some of those can kind of be quantified, some of these not, but they're really more conceptual. For a computer, it's where pixels are, right? It's very specifically placements of pixels. And so there have to be equations, there have to be relationships, weights, that tell the computer sort of when pixels are arranged in this way, it's a cat. When it's not when it's arranged this way, it's not a cat. So you're feeding in images of cats, which is to say basically just whole bunches of pixels in different arrangements. It's transforming it in certain ways, at first randomly, by the way, because you got to start somewhere. And then it puts out a prediction. Cat, not cat. Cat, not cat, right? And you know which ones are cats and which ones are not cats. So every time something comes out the other end, the computer says cat, not cat, cat, not cat, you are matching it up to whether it actually is a cat or not a cat. You put those together, that gives you and somehow you compare the two in a loss function. A loss function basically says how much information was lost. Like you know which images are cats or not cats. That's the information you have. And you're feeding this through the network, through this neural network, and the computer is making certain predictions, and it's not right. In fact, at first it's random, so there's lots of information being lost, and you have to apply some function that allows you to quantify the amount of information that's lost. That generates a score, and that score then has to be fed back. That's back propagation. And there's an optimizer. That oval there is what I'm going to describe on the right. There's an optimizer which gives you some way of adjusting the weights that will be applied to the transformation of data as you feed more images in, so that you lose less information. And that's what's going on. You're just going to sort of spin that wheel over and over and over again. That optimizer is called gradient descent. So for those of you who know calculus, basically what we're trying to do is find a local minimum. That's what calculus is. But we don't know what the equation is, right? And by the way, on the right, I've showed just a simple curve, but in reality, we're dealing with lots of variables. But we just want a simple curve so we can picture it. So we don't know what the equation is, but we're trying to find a local minimum, so we're using this approach, which is called gradient descent. It's called gradient descent because you're sort of going out some and descending some, and going out some and descending some, and then at some point you get to a local minimum. Now, obviously, what we're picturing here is very smooth, right? In reality, who knows what the shape of that is? You don't know ex ante or a priori what the shape of that is, so it's much, much more complicated than the simple picture I'm pasting here. But the concept is, you're going out and you're following mathematical procedures to find a place where you think you've reached a local minimum. Have you reached the absolute minimum? No, but you don't need to. You don't need to absolutely minimize the loss of information. You just need to adjust the weights in some way that you make enough progress that you can just keep going, because the next time you feed more information in, it's going to lose less information and it's going to lose it in different ways. And you can just keep optimizing and keep optimizing and keep optimizing. And then at the end, you've built a set of rules. And that's, in a nutshell, what artificial intelligence, what this type of artificial intelligence using neural networks is. This is the back propagation process that allows you to take your outputs, use it to inform what it's doing so that it works better. Okay, so now we're going to contrast these two flavors of neural networks, machine learning using neural networks, supervised learning and reinforcement learning. Basically, on the left, this is a picture of what we call supervised learning. And you can really think of supervised learning as sort of mapping X to Y. And the basic idea here is you know what the right answer is. So if it's autocorrect for your phone, the right answer is if you accept the word, and the wrong answer is if you go back and delete it, right? If it's an ad targeting program, the right answer is if you click on it, and the wrong answer is if you don't click on it. And on and on and on, right? Whatever it is, you're mapping X to Y, some input to output. And this is basically the process that I described. But we can also have what's called reinforcement learning, which we apply when we don't actually have the right answer. We can just say you're getting closer or you're getting farther away. So an example of this is self-driving cars, right? So like you can't really say like success. I mean, obviously you don't want to hit somebody, right? But it's really tricky to define exactly like what is right or wrong. It's much more closer, farther away. You did a better job, you did a less good job. So what we need to do here, it's more complex. You need to monitor the response of the actions taken. You need to score the response in some fashion so that you're either getting closer to or farther away from the ultimate goal. And it just turns out that where the reinforcement learning process has really been successful so far is with games. Supervised learning, like 95%, I mean, that's not a precise number, but the vast majority of what companies are using artificial intelligence for today is supervised learning. It's where you have a well-defined right answer, wrong answer. The reinforcement learning is an area of tremendous excitement because it could, in theory, be much more generalizable. It's also harder in many ways. But one of the reasons why chess, once again, turns out to be such an important, such a useful problem for computer science is that chess turns out, and Go beforehand, turns out to have been a really good problem to apply reinforcement learning to. So what we can now say, and obviously I'm grossly oversimplifying something very complicated, but how does AlphaZero work? AlphaZero is a reinforcement learning deep neural network that uses repeated self-play to train itself. So the neural network, right, we have to, what is the output? We know what the input is. The input's pretty straightforward. It's the board position. What's the output? So what they developed was a way to have two outputs at the same time. What they called a policy vector and a value score. So the policy vector is an array of expected probabilities. What move the computer expects to be played at each step of the search. And then the value network is the expected outcome of the game at the end. Now, there has to be a search algorithm, right? Because you can't search the whole game. You need to have some way to truncate the tree, because you can't feed in games and tell the computer, oh, just take this one position and play out every single possibility all the way to the end. There has to be a way to truncate that, and it's called Monte Carlo tree search, which we'll get to in a minute, and I'll explain the intuition behind it. I certainly won't be able to explain the math behind it, but I'll explain the intuition behind it. And basically, the reinforcement learning process works as follows, right? The probability weights initially are set randomly. All it knows at the beginning is the rules of the game. And then large batches of games are played running this Monte Carlo tree search algorithm from the current position each turn, right? And so what it does is it just sort of like randomly goes out and so searches. It says, okay, I can't search every game. I can't take a position and search it all the way out to the end, but I'm going to search a lot of it out. That's the Monte Carlo tree search algorithm. And then I'm going to come back. And at first it does it randomly. And at the end of every game, there's a +1, 0, -1, right? Everything's got to be math, right? So win, draw, loss. And then it updates its neural network weights so as to maximize the similarity of its policy vector to the search probabilities and minimize the error between the predicted outcome and the game outcome. And what we see here is it's really quite extraordinary that as it went out, it starts, it doesn't know anything, right? It has an ELO rating of 0, if that's possible. It very quickly gets up to a pretty good level, and then as it keeps playing, thousands and thousands, millions really, right? Because each mini batch is 4,096 training positions, and the x-axis is thousands of those, right? So as it keeps going out, it just gets better and better and better, and in fact even surpasses Stockfish. So let's sort of unpack Monte Carlo tree search. So the underlying intuition here is you want a process that will allow you to take any position and just sort of search all the way out to the end. So remember the way that Stockfish works, or any sort of brute force approach. It takes a set of rules and then it searches sort of everything out each next iteration. As we said, not actually, right? There are some rules for sort of pruning the tree and so forth, but basically conceptually, it's just sort of like it's going out and out and out, sort of like this ever expanding fan. And at some point it hits a horizon. What this AI approach does, what AlphaZero does, is it sort of goes really deep all the way to the end. Of course, it's branching out and out and out and out and out, but it has ways of cutting that tree really viciously and then sort of coming all the way back and updating what it thinks it knows, the various weights, based on the results of that. So you might say, well, at first, well, that's crazy. Like, how could you possibly make progress doing that? But amazingly, it turns out, it takes a lot, it takes millions and millions, but it doesn't take, trillions and quadrillions. It takes enough that makes it tractable. So you can sort of like go out and then come back, and then you go out again and your Monte Carlo tree search has been updated by the weight with the weights that you learned the first time, and you come back and you keep doing that over and over again, and now it turns out that your search is much more intelligent. That's basically what's going on here. And the diagram on the right comes from the paper. I hope you can, I know it's small, I apologize. I hope you can see that diagram. What they are showing here, and by the way, it's a beautiful game. If you haven't played through it, I highly recommend it. It's a lovely game. So AlphaZero is white, and in this position against black, Stockfish, in the first 100 simulations, it is considering up to 10 different candidate moves. Then sort of it goes 10 to third, 10 to fourth, 10 to fifth, so it's each 10 times more simulations. When it does 10 times more simulations the first time, it's really only looking at C6 and D5. And then 10 times more after that, it's still looking at C6 and D5, but now it's weighting D5 more heavily than C6. The number corresponds to its value score, like what it thinks is the probability of winning from the position. So basically, at first it thought it had, if I can read that number correctly, it thought it had a 60% probability of winning this position. But then, pretty quickly it got to a level that it roughly stayed at around 70% probability. And it thought c6 was the best move versus d5. But then actually, as it went farther, it decided d5 was the right move versus c6. And eventually, sort of as it goes out to the end of its, as far as it can go, it settles on d5 as being the right move. And so this is illustrating how the Monte Carlo process is working. Obviously, this is when its function is fully developed, as opposed to when it's training itself, sort of applying sort of at first a random, then very rudimentary, and then sort of continually updating itself to get better and better. Now, here's the funny thing about AlphaZero. Paradoxically, even though AlphaZero produces chess that seems more human-like, it's actually much less transparent. It's a bizarre thing, right? Like, if you've played over the games of AlphaZero versus the games of Stockfish, there's something, I mean, of course, like, Stockfish is amazing, right? Stockfish will crush any human in the world easily. But there's something machine-like about the Stockfish games or any sort of traditional chess program. Whereas the games of AlphaZero, it seems like sort of, I don't know, like, you know, what would happen if God came down and touched Mikhail Tal or something, right? It's like somehow like the superhuman version of the great chess players. It looks somehow more human-like. And yet, for Stockfish, we actually know exactly what it's doing because we built all the rules. I mean, not me or you, but human beings built all the rules. So it's completely transparent what Stockfish is actually doing. But for AlphaZero, what was built was the process for it to generate its own rules. We don't actually know what its rules are. We kind of have to infer what its rules are somehow, but we never really will. Because remember, think back to the sort of image recognition for cat photos, for example. You know, we now have image recognition programs that are very good. They're basically as good at recognizing cat photos as humans are. But in the end, it's basically equations that relate pixels to one another. It's not whiskers and sort of, you know, like it's got this kind of shape of face, and it's not conceptual the way it is with humans. It's not something you can somehow explain. And the same thing is true for AlphaZero and the chess that it's producing. So it's an interesting paradox, and something worth thinking about, I think. There's also, I think, it's really worth thinking about the horizon effect as it manifests with Stockfish and AlphaZero. Now, I assume you all are familiar with this game, right? This is one of the most famous games where AlphaZero beat Stockfish. So this is Queen's Indian, you know, if position on the left. White could have just played knight g4, but instead white played rook e1. And AlphaZero thought after rook e1, it had a small advantage, but not a big advantage. So it had a probability score somewhere sort of, I think, in the upper 50s, maybe. Whereas AlphaZero is like, well, I'm winning a knight. And yes, of course, it has rules for, like, it knows its kings is exposed and it's behind in development and so on and so forth. But according to its rules, it just has a big advantage in the position, and it's looking out as far as it can, and it can't see sort of how it's going to lose. Now, much further on in the game, apologize for this being cut off down below, but much further off in the game, we reached this position on the left, and white played like this really incredible move, c4. It's just, God, it's beautiful. I mean, it's just like, it's just such a beautiful move. It turns out like there's no obvious way for white to intensify the attack, and c4 just like turns out to be like this really powerful move because it's threatening to open up the c file, which opens up this new line of attack. It cuts off the queen. It just sort of like it uses that little last ounce of force in the position to pry it open. Now, there's no earthly way that Stockfish could have seen this position when it was considering capturing the knight. Like, it's so far beyond its horizon, it's laughable. But it's perfectly possible. Remember the Monte Carlo tree search process, right? Like AlphaZero goes really deep. It's pruning like crazy. It's going really deep. It may very well have seen this position. So in some sort of very strange sense, we're seeing the horizon effect manifest itself again. But at the same time, the Monte Carlo tree search process has its own weakness, right? And I didn't put it here because it was just too difficult to try to show. But there's apparently in the earlier iteration that played the Go match against Lee Sedol. I don't know Go well enough to be able to verify this. I've just read that apparently it in the one game that it lost, it made a very peculiar kind of error. And the error that it made seems to have been due to an earlier iteration of the way its Monte Carlo tree search process worked. There was also a game that it lost against Stockfish. And in that game, obviously, it won most of the games against Stockfish, but there was one endgame where it was one of these sort of like good knight versus bad bishop endgames. And basically, like, there's no way you could lose this position if all you just wanted to do was sort of putter around. And what it did was it sort of went for this attempt to win. But it seems to have just missed this kind of long, narrow, single path where, in fact, this way of attempting to win lost, right? It actually like jettisoned a pawn and tried too hard to win. It's kind of like almost of the human like trying too hard to win, but in this case, it's a particular feature of its Monte Carlo tree search process. So it's possible that we will see weaknesses or shortcomings of the artificial intelligence approach that AlphaZero uses. Going back to the cat imaging. This is a well-known phenomenon in other kinds of AI applications where you can take an image that to human eyes literally cannot be distinguished between another image. So you have sort of cat, and it just like literally looks like they're exactly the same photo. But in fact, what you've done is you've just changed a few pixels. And it turns out that like it thinks one is a cat and like one is a horse or something. It's like you get like very strange outcomes like that because there's something about the weighting of these of this function that leads itself open to these sort of like narrow weaknesses, these sort of like chinks in the armor, you could almost think about it. That's very difficult to understand, right? Because remember, it is this kind of black box. Like diagnosing this and trying to anticipate it seems to be very difficult. So anyway, that's the end of my comments, and I'd be happy to take any questions or just talk about it. I think artificial intelligence itself is super exciting, and I think it's the most exciting thing to happen in chess in a long, long time. I think we're just at the beginning of seeing how it's going to affect chess.
Thank you.